There is a theory in physics so strange, so quietly unsettling, that many scientists approach it with hesitation. Not because it's nonsense, not because it lacks mathematics, but because if it's true, it gently reshapes how we understand our place in reality. The idea is simple to state and difficult to absorb. What if our universe began inside a black hole? Not as a metaphor, not as science fiction, but as a genuine possibility suggested by the equations of physics. In this view, the Big Bang was not the beginning of everything. It was the beginning of our universe. A moment that, from another perspective, may look like the formation of a black hole. From the inside, that event appears as expansion, as space and time unfolding, as a universe growing larger and older. From the outside, if such an outside exists, it might appear as something far quieter, a dark region, a boundary, an event horizon. And just as nothing escapes a black hole from within, nothing beyond our observable universe can ever reach us. Tonight we'll explore why the mathematics describing black holes and the mathematics describing the early universe are unexpectedly similar. Why the edge of what we can see behaves like a cosmic horizon. And why some physicists, including thinkers like content reference oecite 0, index equals 0, have wondered whether black holes might give birth to new universes. In this picture, universes don't appear once. They appear many times, each one nested inside another, a quiet chain of creation, unfolding beyond observation. This isn't about fear, it's about perspective. Because if our universe is inside a black hole, then we are not trapped. We are simply part of a much larger structure, one that is calm, vast, and mostly beyond our concern. Tonight, we're not here to be disturbed by the idea. We're here to gently explore it, to let the universe feel a little larger, and our place within it a little quieter. Science doesn't usually start with philosophy. It starts with numbers, equations, mathematical descriptions of physical reality that either match observations or don't. And when the math works, when equations accurately predict what we observe, we take those equations seriously, even when they lead us somewhere uncomfortable. The uncomfortable place this particular math leads us is inside a black hole. Let me take you back to the early 20th century, when Einstein published his theory of general relativity. This wasn't just a new theory of gravity, it was a completely new description of space, time, and how matter shapes the fabric of reality. Before Einstein, space was just the backdrop against which events happened. After Einstein, space and time became active participants, bending and warping in response to mass and energy. The equations of general relativity are beautiful in their elegance and terrifying in their implications. They describe how matter curves space-time, how curved space-time tells matter how to move, how gravity is not a force pulling objects together, but the geometry of space itself guiding objects along curved paths. And when physicists took these equations seriously, really seriously, following them to their logical conclusions without flinching, they found something disturbing. The equations predicted objects so massive, so dense, that space-time would curve completely around them. Objects from which nothing could escape. Not matter, not light, not information of any kind. Black holes. Not hypothetical curiosities, mathematical inevitabilities. If general relativity is right, and we know it's right because it's been tested to extraordinary precision, then black holes must exist. The math demands them, and the math describes them in precise detail. It tells us about event horizons boundaries around black holes, beyond which nothing can return. It tells us about singularities, points of infinite density at the center where the mathematics breaks down, where the equations produce infinities that signal something fundamentally wrong with our description of reality. It tells us about how time behaves near black holes, slowing down as gravity increases, stopping completely at the event horizon. This is all well-established physics, uncontroversial, confirmed by observation. We've seen black holes' gravitational effects. We've detected gravitational waves from black hole mergers. We've photographed the shadow of a supermassive black hole with connected telescopes spanning the entire Earth. Black holes are real. The math describes them accurately. No physicist disputes this. But then a strange thing happened. When physicists looked carefully at the equations describing the interior of black holes, the region inside the event horizon, they noticed something unsettling. The mathematics describing what happens when matter collapses into a black hole, when it crosses the event horizon and falls toward the singularity, looked familiar, disturbingly familiar. Because those same mathematical structures, the same forms, the same relationships between variables, the same patterns in the equations appeared in a completely different context. In the equations describing the Big Bang isn't just an explosion. It's a mathematical singularity, a point where the equations of general relativity break down, where density becomes infinite, where the concept of before becomes meaningless. The universe began in a state of infinite density, and it expanded from that point, cooling and evolving into the cosmos we observe today. Sound familiar? A singularity, infinite density, a point where the equations break down, expansion from that point. That's also what happens inside a black hole. Matter falls toward the singularity. Density increases. At the singularity, the equations break down. And in the region beyond, inside the black hole, space and time behave differently than they do outside. The mathematical similarity isn't superficial. It's deep, structural, fundamental. The same equations describe both situations. Not approximately, not metaphorically, literally the same mathematical framework, describing what appear to be two different physical situations in ways that are suspiciously similar. This is what started the serious scientific discussion. Not philosophy, not speculation, not wild imagination. Math, the equations themselves seem to be suggesting something. Maybe these two situations, the interior of a black hole and the Big Bang, aren't different situations at all. Maybe they're the same situation viewed from different perspectives. Maybe the Big Bang was what a black hole looks like from the inside. Consider what we know about the observable universe. It has a boundary, not a physical wall, but an edge beyond which we can't see. This boundary exists because the universe has a finite age. Light travels at a fixed speed, and the universe hasn't existed long enough for light from beyond a certain distance to reach us. Beyond that boundary, for all practical purposes, nothing exists in our observable cosmos. Now consider what we know about black hole event horizons. They're boundaries beyond which information can't escape. Inside an event horizon, you can receive information from outside light and matter fall in, but nothing can get out. The event horizon is an asymmetric boundary, allowing information to flow in one direction but not the other. Our observable universe boundary is similar. We can see light that has traveled toward us from distant regions, but we can't receive information from beyond our cosmic horizon. And we can't send information outside our observable universe either, not because of a physical barrier, but because the universe is expanding too fast for signals to ever bridge that gap. Both are horizons, both are information barriers, both are boundaries that separate here, where physics works normally, from there, where we simply don't know. And both arise from similar mathematics. But it goes deeper than just the boundary. When physicists study the thermodynamics of black holes, the way black holes behave as thermodynamic systems with temperature and entropy, they find mathematical structures that mirror cosmological thermodynamics. The way information is distributed in a black hole mirrors the way information is distributed in a universe. The way black holes evolve over time mirrors, in certain respects, the way universes evolve. These aren't coincidences. In physics, when equations describing two different systems turn out to be identical or very similar, it usually means something. It usually means those systems are related, that they're different manifestations of the same underlying physics, different aspects of the same fundamental reality. And the mathematical relationship between black holes and the Big Bang is too detailed, too structural, too precise to be coincidental. The physicists who noticed this, and they were serious physicists, not fringe theorists, had to ask, what does this mean? What is the mathematics telling us? One possibility. The mathematics is telling us something about the structure of reality that we haven't fully understood yet. That black holes and Big Bangs are related phenomena connected by the same underlying physics, and understanding one will help us understand the other. Another possibility, the more radical one, the one we're exploring in this video, is that the mathematics is telling us something more literal. That black holes and Big Bangs aren't just mathematically similar, that they're actually the same thing. That when a black hole forms in our universe, a new universe begins on the other side. That our own universe exists on the other side of a black hole in some larger cosmos. The math doesn't prove this. It doesn't definitively show that our universe is inside a black hole. What it does is suggest it powerfully, persistently, uncomfortably. It raises the possibility in a way that can't be dismissed because the equations themselves are the evidence. And in physics, when the equations suggest something, we have to take it seriously. Especially when it's uncomfortable. Even when it challenges everything we thought we knew about where we are. The math started this conversation, and the math doesn't let us close it easily. Because once you notice the similarity, once you see how closely the interior of a black hole resembles the beginning of a universe, you can't unsee it. The equations are right there, making the comparison unavoidable. The mathematics of our universe's birth looks like the mathematics of falling into a black hole, which raises the question, is that a coincidence? Or is it a description? Did you know about the mathematical connection between black holes and the Big Bang before watching this? Does math alone feel like enough evidence to take this theory seriously? Share your thoughts below. 2. Black holes and Big Bangs. Let's go deeper. The mathematical similarity we discussed isn't just an abstract curiosity. It has physical implications that are genuinely disturbing. Because if the math connecting black holes and Big Bangs is telling us something real, something physical, then we need to understand exactly what that connection means. And to do that, we need to understand what black holes actually do. Not just what they are, dense, dark, inescapable, but what they actually do to space and time, what happens when matter collapses into one, and why that process looks so much like the beginning of a universe. When a massive star dies, its core collapses. The outer layers explode in a supernova, but the core, if it's massive enough, has nowhere to go. Gravity overwhelms every other force. Atoms collapse. Electrons are crushed into protons, forming neutrons. Neutron star forms. But if the mass is large enough, even that isn't enough. Neutron degeneracy pressure, the quantum mechanical resistance that holds neutron stars together, gets overwhelmed. The collapse continues, and then something remarkable happens. The matter compresses to a point where space itself curves completely around it. The curvature becomes so extreme that space closes, creating a region from which nothing can escape. The event horizon forms. A black hole is born. Now, here's the question that physicists started asking. What happens to all that matter? The star's core, compressed beyond neutron density, still has mass, still has energy. Conservation laws, some of the most fundamental principles in physics, say that energy can't just disappear. Matter can't simply cease to exist. Whatever fell into the black hole has to go somewhere. But where? Inside the event horizon, space-time is so warped that all paths lead toward the singularity. There's no way to stop the collapse. The matter falls inexorably toward the center, where density becomes infinite and the equations break down. At the singularity, physics, as we know it, fails. The mathematics produces infinities, which is a polite way of saying we don't know what's actually happening. General relativity breaks down. Quantum mechanics should take over, but we don't have a complete quantum theory of gravity. The singularity is a gap in our knowledge, a place where our best theories simply stop working. And here's where the black hole universe theory becomes compelling. What if the singularity isn't the end? What if it's the beginning of something else? Think about what we know about the Big Bang singularity. Our universe began in an incredibly hot, dense state of singularity where the equations of general relativity break down in exactly the same way. The universe then expanded from that singularity, cooling and evolving over billions of years into the cosmos we inhabit. If black hole singularities and Big Bang singularities are the same type of mathematical object, and they appear to be, then maybe they're the same physical object too. Maybe a black hole singularity isn't a point where matter is destroyed, but a point where matter transitions into a new universe. Maybe the collapse into a black hole singularity in our universe is, from another perspective, a Big Bang in a new universe. This idea that black holes create universes, that singularities are transition points rather than endpoints, was formalized by physicist Lee Smolin, but the mathematical groundwork was laid by others. And the more seriously physicists looked at it, the more the mathematics supported the basic concept. Consider what we know about conditions inside a black hole after it forms. The singularity exists, but matter is falling into it. The interior of the black hole isn't static, it's dynamic. And the dynamics of matter in the extreme conditions near a singularity might create exactly the conditions needed to initiate expansion. Think of it this way. Matter falling into a black hole gets compressed to extreme densities. At some point, quantum effects, which we know must become important at extreme densities, even though we don't fully understand them, might create a repulsive force. This is similar to what cosmologists call inflation in our own universe's early history, a period of exponential expansion driven by a repulsive energy field. If quantum effects near the singularity create a repulsive force, matter might not pile up at a point of infinite density. Instead, it might bounce a big bounce, as some physicists call it, transitioning from collapse to expansion. From the perspective of whatever exists in that new expanding region, this bounce is a big bang. A universe is born. And that new universe wouldn't be visible from ours. It would be entirely inside the black hole's event horizon, causally disconnected from everything outside. The new universe could grow arbitrarily large, expanding for billions of years, and from our perspective, it would still be inside the black hole. The two universes would never interact, never communicate, never know about each other. This is the key insight. Size in the interior of a black hole isn't the same as size in the exterior. The interior geometry is different dramatically, fundamentally different. A black hole might appear tiny from outside, just a few kilometers across, while its interior contains a universe billions of light years in extent. Interior and exterior are different regions of space-time, connected at the event horizon, but otherwise separate. If this seems paradoxical, it's because we're used to thinking about space as uniform, the same everywhere, with distances meaning the same thing throughout. But general relativity tells us space is dynamic, curved, different in different places. The interior of a black hole isn't just inside an object in the ordinary sense. It's a different region of space-time with its own geometry, its own time, potentially its own physical laws. And if black holes create universes, our universe being inside a black hole becomes not just possible, but expected. We live in a universe with billions of galaxies, each containing billions of stars. Many of those stars will end their lives as black holes. We estimate our galaxy alone contains millions of stellar mass black holes, plus the supermassive one at its center. If each black hole creates a universe, then our universe has already spawned millions of child universes. And our universe itself was spawned by a black hole in some parent universe. And that parent universe was spawned by a black hole in a grandparent universe. The cosmic family tree extends infinitely in both directions, ancestors and descendants. Nested universes, each one inside a black hole that's inside a universe that's inside another black hole. But wait. If black holes in our universe have already created millions of child universes, those universes might themselves contain black holes, which created their own child universes. The number of universes grows explosively, each generation more numerous than the last. It's a cosmic population explosion, a universe of universes, an infinite multiverse generated not by quantum probability, but by gravitational collapse. And here's the really unsettling part. We can't see any of it. We can't detect child universes inside our black holes. We can't communicate with our parent universe. We're completely isolated, causally disconnected from the rest of this vast cosmic structure. We know only our universe, only the region inside our particular event horizon, completely unaware of the larger structure we're embedded in. We're inside a black hole, but we can't see the event horizon because we're inside it. We can't see the parent universe because nothing from outside can penetrate in. We can't even tell from inside our universe whether this theory is true, because the evidence that would confirm it is on the other side of the event horizon, forever inaccessible. We're sealed in, not violently, not dramatically, just geometrically. The structure of space-time ensures our isolation. The event horizon isn't a wall we could detect or a barrier we could probe. It's just the boundary of our causal future, the limit of what we can affect and be affected by. And that's what makes this theory so philosophically disturbing. It's not just that we might be inside a black hole. It's that being inside a black hole looks exactly like what we experience. Our universe is closed in the sense that there's a horizon beyond which we can't see. Our universe began in a singularity. Our universe's early expansion resembles what would happen if quantum effects bounced a collapsing black hole. Every feature of our universe that we think we understand might be, from another perspective, just the features of a black hole's interior. We look at the Big Bang and see a beginning. Someone outside in the parent universe looks at a black hole and sees nothing remarkable. Just another collapsed star, another black hole, one of many in their universe. They wouldn't know there's a cosmos inside. They couldn't know. The event horizon prevents information from escaping. Our universe, with its billions of galaxies and trillions of stars, and at least one planet with life looking back at everything and wondering, all of that is invisible from outside, sealed behind an event horizon, contained within what looks, from outside, like just another black hole. We might be someone else's black hole. We might be the inside of a collapsed star in another universe, our entire existence fitting inside what another civilization sees as a point-like singularity. And we'd never know, because the evidence is on the other side of the event horizon. That's not a comforting thought, but it might be true. If our universe is inside a black hole, does that change how you feel about existence? Does it make the universe feel smaller contained, or does the idea of infinite nested universes make it feel larger? Tell us below. There's a boundary around our universe. Not a physical wall, not a barrier you could touch or see or detect with instruments, but a boundary nonetheless, a horizon, beyond which we cannot see, cannot reach, cannot communicate. A limit to our observable universe that is, in several important ways, mathematically identical to the event horizon of a black hole. And if we're inside a black hole, this boundary isn't just the edge of what we can see. It's our prison wall, the structure that ensures we can never leave, never communicate with the outside, never even confirm that an outside exists. Let's talk about what this horizon actually is, why it exists, and why it looks so disturbingly like an event horizon. Our universe has a finite age. It began a specific amount of time ago in the hot, dense state we call the Big Bang. Light travels at a fixed speed, the fastest anything can travel, the ultimate speed limit of the universe. Because our universe has a finite age and light has a finite speed, there's a maximum distance from which light has had time to reach us. Beyond that distance, light hasn't had time to reach us yet. Not because it isn't trying light from those distant regions is traveling toward us right now, but because the universe simply hasn't existed long enough for that light to make the journey. Those regions are beyond our cosmic horizon. We can't see them. We can't detect them. We have no information about what's there. This is our observable universe, the sphere of space from which light has had time to reach us since the Big Bang. It's enormous by human standards, incomprehensibly vast. But it's finite. It has a boundary, and beyond that boundary is a region we call the unobservable universe regions that exist, probably, but that are causally disconnected from us. Now here's where it gets interesting. In a static universe, one that wasn't expanding, this horizon would gradually recede as the universe aged. Over time, light from more and more distant regions would reach us, expanding our observable universe, revealing more of what exists beyond our current horizon. But our universe isn't static, it's expanding. And it's not expanding at a constant rate, it's accelerating. Dark energy is pushing space apart faster and faster, so that distant regions are receding from us at increasing speeds. Beyond a certain distance, regions are receding so fast that light from them will never reach us, even given infinite time. The expansion carries them away faster than light can close the gap. This means our observable universe isn't just limited by age, it's fundamentally limited by expansion. There are regions right now actually existing, containing matter and stars and possibly life that are forever beyond our reach. Not just currently unobservable, but permanently, irrevocably unobservable. No matter how long we wait, no matter how advanced our technology, their light will never reach us because space between us is expanding too fast. This permanent boundary, the cosmological event horizon, behaves remarkably like the event horizon of a black hole. Information can come in from inside the horizon, but information from beyond the horizon can never reach us. We're surrounded by a sphere beyond which we're causally isolated, unable to send or receive signals, unable to interact in any way. And like a black hole's event horizon, our cosmic horizon has thermodynamic properties. Black hole event horizons have temperature Hawking temperature and entropy proportional to their surface area. Cosmological event horizons also have temperature, the Gibbons-Hawking temperature, and entropy. The mathematical structures describing both are almost identical. This isn't coincidence. It's not analogy. The same physics governs both. The same mathematical framework describes both a black hole's event horizon and our universe's cosmological horizon. Whatever physical principles determine one seem to determine the other. So we're surrounded by an event horizon. Not a black hole's event horizon, we're inside something, not outside it. But a horizon that functions the same way, isolating us from everything beyond, preventing information exchange with the region outside, creating a causally closed sphere that we can never escape. And like someone falling into a black hole who crosses the event horizon without noticing anything special, without seeing a wall or feeling a barrier, we can't detect our cosmic horizon by looking at it. You can't see it because light from beyond, it never reaches us. You can't feel it because it's not a physical barrier. You can't detect it instrumentally because any instrument you point in its direction would see the same universe you see everywhere else, just very distant. The horizon is invisible, and yet it's there, surrounding us, enclosing us, defining the limits of our existence. Now, there's something deeply unsettling about this that goes beyond just knowing you can't see everything. It's about what the horizon implies about our knowledge of reality. Right now, beyond our cosmic horizon, events are occurring. Stars are being born. Galaxies are colliding. Planets might be forming. Life might be evolving. An unfathomable amount of reality exists beyond our horizon, more than we could ever observe, more than we could ever know about. And we will never have any information about it. Not just now, never. No technology will bridge that gap. No future advance in astronomy will pull those distant regions into our observable universe. The horizon is fixed by the laws of physics themselves. Information from beyond it cannot reach us because space expands too fast for it to make the journey. We're informationally isolated. What we can observe is all we'll ever observe. The universe has hidden itself from us behind a horizon we can't penetrate, and we're left with a bubble of observable cosmos that's large by human standards, but tiny compared to the full extent of reality. This is exactly what being inside a black hole would feel like. From inside a black hole, if you could somehow survive and think, you'd be surrounded by an event horizon you couldn't see or detect directly. Light from outside would fall through the horizon, so you could see into the outside universe, but you couldn't communicate out. You couldn't escape. You'd be informationally isolated, contained in a region of space-time with a boundary you can't cross. That's our situation. We can see light falling into our observable universe from beyond the horizon. We receive signals from distant regions that were once closer, that emitted light before expansion carried them beyond reach. But we can't send signals out. We can't escape. We can't cross our cosmic horizon any more than matter can cross a black hole's event horizon outward. We're contained, enclosed, not violently, not dramatically geometrically. The structure of our space-time puts us inside a horizon, and nothing about that structure allows us to get out. And here's what makes this particularly disturbing when combined with the theory that we're inside a black hole. If we're inside a black hole's event horizon, then our cosmic horizon might be the same thing as the black hole's event horizon, just viewed from the inside. The boundary that defines the limits of our observable universe, and the boundary that defines the black hole in the parent universe might be the same surface, two descriptions of the same geometric feature, one from inside and one from outside. From outside in the parent universe, the event horizon is the point of no return, the boundary beyond which things fall into the black hole and don't come out. From inside our perspective, it's the cosmic horizon, the edge of our observable universe, the limit beyond which we can't see. Same surface, two perspectives, two completely different descriptions of the same feature, one from each side. This means our cosmic horizon isn't just a limitation on what we can observe. It might be the actual event horizon of the black hole we're inside. The wall of our prison isn't somewhere far away. In the parent universe, it's right at the edge of our observable universe, the furthest point we can see. Everything beyond our horizon isn't just unobservable universe. It might be the parent universe, the external cosmos, the region outside our black hole. And the horizon isn't just the limit of what we can detect. It might be the actual boundary between inside and outside, between our universe and whatever contains us. We're not looking out at distant parts of our own universe when we look toward the horizon. We might be looking at the wall that separates us from an entirely different cosmos. And that wall is impassable, not because we lack the technology, because physics prevents it. Information cannot cross from inside a black hole's event horizon to outside. If we're inside a black hole, we're sealed in forever, with no possibility of escape, no possibility of communicating with whatever exists outside. Our prison walls are made of space-time itself, not solid, not visible, not detectable, but absolutely, mathematically, physically real. And we've been inside them since the moment our universe began. Nobody told us we were in prison because nobody knew. Because from inside the prison, things look normal. The laws of physics work. Space extends as far as we can see. Time passes. Things happen. It just happens to all be happening inside a black hole. The cosmic horizon isn't just the edge of what we can see. It might be the most important boundary in existence, the line between our universe and whatever lies beyond, the wall of the container we've been living in since the Big Bang, the event horizon of the black hole that is our universe. We are enclosed. We've always been enclosed. And no amount of technology or exploration will change that. Because you can't escape a black hole's event horizon from the inside. And if our universe is inside one, we can't escape either. We're home. And home is a prison, and it's made of space-time. Does the idea that our cosmic horizon might be a black hole's event horizon change how you feel about the universe's size? Are we in a vast cosmos or a small cell? What do you think? So far, we've been talking about mathematics, equations that look similar, boundaries that behave identically, physical processes that mirror each other across different scales. These are compelling observations, but they're passive. They suggest a connection without explaining why that connection exists or what it means for the universe as a whole. Lee Smolin took the next step. He asked not just whether universes form inside black holes, but why. What purpose does this serve? What does it mean for the universe as a system? And in doing so, he proposed one of the most radical and fascinating theories in modern cosmology, one that transforms our understanding of not just where we are, but why we are. Smolin is a theoretical physicist, one of the founders of loop quantum gravity, a serious scientist at a serious institution, not a fringe theorist, not a philosopher dreaming up unprovable ideas. A physicist who looked at the mathematics, took the black hole universe connection seriously, and asked what happens if you follow it to its logical conclusion. His conclusion was extraordinary. The universe evolves, not just in the sense that it changes over time, we knew that, but in the sense that it reproduces, varies, and is subject to selection. In the sense that natural selection, the mechanism Darwin identified for biological evolution, applies to universes themselves. Smolin called this theory cosmological natural selection, and it's worth understanding in detail because it changes everything about how we think about our universe's properties, its laws, and why it is the way it is. Start with the basic premise we've already established. Black holes create new universes. When a black hole forms in our universe, a new universe spawns inside it. That new universe expands, evolves, and potentially forms its own black holes, each of which spawns another new universe. So universes reproduce through black holes. Each black hole in a parent universe creates a child universe. The child universe grows, evolves, potentially creates its own black holes, which create grandchild universes. The family tree of universes grows exponentially. Now add variation. Smolin proposed that when a new universe forms inside a black hole, its physical constants, the fundamental numbers that determine how physics works, change slightly from the parent universe. Not drastically, not randomly in a way that could produce anything at all, but small mutations, slight variations in the values of constants like the strength of gravity, the mass of electrons, the strength of the nuclear forces. This is the crucial step. In biology, reproduction comes with variation. Offspring are similar to parents but not identical, with small random differences. If universes reproduce with variation, with each child universe having slightly different physical constants than its parent, then you have the raw material for evolution. Because not all physical constants are equally conducive to black hole formation. Some values of the constants produce universes that form many black holes. Others produce universes that form few or none. A universe with slightly different gravity might not form stars at all, and without stars, no stellar mass black holes. A universe with different nuclear forces might not allow atomic nuclei to form. No atoms, no chemistry, no planets, no stars, no black holes. Physical constants that allow black holes to form are successful in the evolutionary sense. They produce offspring universes. Constants that don't allow black holes are evolutionary dead ends. Those universes exist but don't reproduce. Over many generations of universe reproduction, a selection pressure emerges. Universes with constants that produce lots of black holes have lots of offspring. Those offspring with similar but slightly varied constants also produce black holes and have offspring. Over cosmic generations, not years or millennia, but universe lifetimes, the population of universes shift toward those with constants optimized for black hole production. This is natural selection operating on universes. Not designed, not guided, not intentional, just the blind, mechanical process of variation and differential reproduction playing out across cosmic scales. The same process Darwin identified in biology, operating not on organisms but on universes themselves. And here's the prediction that makes this theory scientifically valuable rather than just philosophically interesting. If our universe evolved through this process, if it's been selected for black hole production, then our physical constants should be near optimal for forming black holes. Not perfect evolution never produces perfection, just good enough to reproduce, but close to optimal. Small changes to our physical constants should reduce the number of black holes our universe can form, because evolution should have pushed the constants toward a local maximum of black hole productivity. This is testable. We can ask, if we changed our physical constants, slightly made gravity a bit stronger or weaker, adjusted the nuclear forces, would we get more or fewer black holes? If Smolin is right, we should get fewer. Our constants should be in a region where they're near optimal for black hole formation. When physicists did this analysis, they found something striking. Our physical constants do appear to be near optimal for forming black holes. Small variations in several fundamental constants would reduce black hole formation. The constants seem tuned not perfectly, but substantially toward maximizing black hole production. This is interesting for several reasons. 1, it confirms a prediction of the theory. 2, it provides a natural explanation for the fine-tuning problem, the observation that our physical constants seem suspiciously well-suited for complex structures like stars and life. The fine-tuning problem has long puzzled physicists and philosophers. Our constants seem to be in a narrow range that allows complex chemistry, stars, planets, and life. Change them significantly, and the universe becomes sterile. No atoms, or no stars, or no chemistry, or no nuclear reactions. This fine-tuning seems to demand explanation. Why should the constants be in this narrow range? The usual answers are unsatisfying. Random chance? The probability of randomly landing on constants that allow complexity is astronomically small. Divine design? That's not physics. The anthropic principle: we observe these constants because we couldn't exist to observe any others. That's circular reasoning. Smolin's cosmological natural selection offers a different answer. The constants aren't randomly chosen, and they're not designed. They evolved. Over many generations of universe reproduction, selection pressure pushed the constants toward values that maximize black hole formation. And crucially, the conditions that maximize black hole formation are similar to the conditions that allow complex structures, stars, and life. Black holes form from massive stars. For massive stars to form, you need the right atomic physics, the right nuclear forces, the right gravitational dynamics. The same conditions that produce black holes also produce the rich chemistry and stable stellar environments that allow life to evolve. Life is, in a sense, a side effect of black hole optimization. Our universe is good for life because it evolved to be good at making black holes, and making black holes requires the kind of complex astrophysical environment where life can also emerge. This is a profound reframing. We've long wondered why the universe seems suited for life. The answer might be, it's not, primarily. It's suited for black holes. Life is just along for the ride, a consequence of the same conditions that make black holes abundant. There's something both humbling and liberating about this. Humbling because we're not the point black holes are. Life didn't emerge because the universe was designed for it. Life emerged because the universe was selected for black hole production, and the two happen to require similar conditions. We're incidental, but liberating because it removes the mystery. We don't need to invoke design or fine-tuning or anthropic reasoning. We just need evolution. The same blind process that produced complex life on Earth produced complex universes in the multiverse. No intention required. No designer necessary. Just variation, reproduction, and selection. Smolin's theory also makes other predictions. If our universe is a member of an evolved population, it should be typical of that population, not radically unusual, not a bizarre outlier. It should have roughly the same properties as most other universes in the evolved multiverse. We can't test this directly. We can't observe other universes. But we can ask whether our universe seems unusual or typical for a universe optimized for black holes. And the answer seems to be roughly typical. Our universe is good at making black holes. It has billions of galaxies, each with billions of stars, many of which end their lives as black holes. The black hole population of our universe is enormous. From an evolutionary perspective, our universe is a successful reproducer, not the most successful possible. We could imagine universes with even more black holes, but successful enough to have been selected to be part of the evolved population rather than an evolutionary dead end. There are objections to Smolin's theory. The mutation mechanism, the idea that physical constants change slightly at each black hole formation, isn't derived from any established physics. It's an assumption necessary for the theory, but not yet grounded in a deeper theory that explains why constants would change. Also, if constants change with each generation, the population of universes might drift away from any particular value over time, rather than converging toward optimal values. The selection dynamics might be more complex than Smolin assumed, and of course the theory is very hard to test. We can't observe other universes. We can check whether our constants seem near optimal for black holes, and they do, but near optimal is hard to quantify precisely, and the comparison requires assumptions about what other universes would look like. Despite these objections, Smolin's theory has influenced serious discussions in cosmology and philosophy of physics. It offers something rare in cosmology, a naturalistic explanation for fine-tuning that doesn't require a multiverse of randomly generated universes or an appeal to design. Instead, it gives us universes that evolve, that get better at reproducing, that accumulate properties conducive to structure and complexity through the same elegant mechanism that drives biological evolution. The universe is alive, in a sense, not conscious, not intentional, but participating in a process that looks remarkably like life. Reproduction with variation, selection for reproductive success, accumulation of adaptive properties over generations, and we're not the products of design or chance. We're the products of cosmic evolution, descendants of a long line of universes that got better and better at making black holes, until they made one that also made us. We're inside a black hole, but we're also the children of black holes. Conceived in stellar collapse, born in quantum bounce, evolved over cosmic generations to be exactly what we are. That's not just a physical theory. That's a creation story. And unlike most creation stories, it's grounded in mathematics. Does cosmological natural selection make the universe feel more meaningful, like we're part of an evolutionary process, or less meaningful, knowing we're just a side effect of black hole production? Tell us what you think. Black holes swallow everything. Matter, light, information. Anything that crosses the event horizon falls in and doesn't come out. That's the definition. That's what makes them black holes. The one-way nature of the event horizon is fundamental, baked into the mathematics, confirmed by observation. But mathematics is symmetric in ways that physics sometimes isn't. And when physicists looked carefully at the equations describing black holes, they found something unexpected hiding in the math. Something that had been there all along, ignored, dismissed, treated as a mathematical curiosity with no physical meaning. They found the opposite of a black hole. A white hole is what you get when you run the equations of general relativity backwards. Where a black hole has an event horizon that matter and light can cross inward but not outward, a white hole has an event horizon that matter and light can cross outward but not inward. Where a black hole absorbs everything, a white hole emits everything. Where a black hole's interior is a region you can enter but never leave, a white hole's interior is a region you can leave but never enter. A white hole is an object that expels matter and radiation continuously without anything going in, a source rather than a sink, creation rather than destruction, an object that produces rather than consumes. When physicists first derived white holes from the equations, the response was mostly dismissal. Sure, the math allows them. The math also allows all sorts of things that don't exist in reality. White holes seemed unphysical. There was no obvious mechanism for creating them, no process that would produce a region of space-time with that particular geometry. They were mathematical ghosts, valid solutions to equations, but unlikely to correspond to anything real. But then people started thinking more carefully about what happens inside black holes, and the dismissal became harder to maintain. Here's the thing about black hole singularities, their problems. Mathematical infinities, places where our theories break down, signals that something is missing from our understanding. Physicists generally believe that singularities aren't real, that they're artifacts of using theories beyond their domain of validity. When quantum gravity is properly understood, singularities will be replaced by something finite, something physical, something that the equations of quantum mechanics and general relativity together can describe. What might that something be? One proposal, developed by several physicists over recent decades, is that the singularity bounces. Instead of matter collapsing to infinite density and stopping there, quantum effects create a repulsive force near the Planck density, the density at which quantum gravitational effects become dominant. This repulsive force halts the collapse, reverses it, and initiates expansion. From outside the black hole, this bounce is invisible, hidden behind the event horizon, causally disconnected from the external universe. But from inside, from the perspective of the infalling matter, it's dramatic. Collapse reverses to expansion, density decreases, space expands outward. And the mathematical description of this bouncing region? It's a white hole. The interior of a black hole after the bounce is mathematically equivalent to a white hole interior. The expanding region inside the black hole, the new universe spawning from the quantum bounce of the singularity, looks from the inside like matter and space emerging from a white hole. Creation, expansion, a Big Bang. This means the Big Bang, our Big Bang, the event that started our universe, might be a white hole. Not a white hole in the sense of the mathematical curiosity that physicists dismissed, but in the sense of the expanding interior of a black hole after quantum bounce. The beginning of our universe, the most important event in cosmic history, might be described by exactly the mathematics physicists had been ignoring. Let's sit with this for a moment. The Big Bang singularity is one of the great unsolved problems in physics. What happened at the beginning? What was there before? What caused the expansion? General relativity breaks down at the singularity, and we don't have the quantum theory of gravity needed to describe what actually occurred. But if the Big Bang is a white hole, if it's the quantum bounce of a collapsing black hole in a parent universe, then we have a different perspective on those questions. What happened at the beginning? A black hole formed in the parent universe. What was there before? The parent universe, and within it, the star whose collapse created our black hole. What caused the expansion? The quantum bounce that occurs when collapsing matter reaches maximum density and reverses. These aren't complete answers. We still need the quantum theory of gravity to work out the details, but they're a framework, a context, a way of understanding the Big Bang, not as a mysterious beginning from nothing, but as a transition, the other side of a black hole formation. And white holes have another property that's relevant here. They emit matter and radiation. Not from some internal source. White holes don't create matter from nothing. Rather, the matter that was inside the black hole when it formed comes out through the white hole. From outside a white hole, you'd see matter and radiation being expelled, appearing to come from nowhere, emerging into space. From the outside of a white hole, this looks like a source. From the inside, from within the expanding white hole region, it looks like a beginning, a Big Bang, matter appearing and expanding outward. The matter in our universe didn't appear from nothing at the Big Bang. If the Big Bang is a white hole, that matter came from somewhere, from the star that collapsed in the parent universe, from whatever fell into the black hole before our universe formed. The Big Bang wasn't creation from nothing. It was creation from something from the matter of a parent universe, transformed and expelled through the quantum bounce. This resolves one of the most troubling aspects of the Big Bang. Where did all the matter come from? From the parent universe. Conservation of energy is maintained across the boundary. The energy that went into the black hole in the parent universe becomes the energy of the new universe. Nothing is created from nothing. Everything comes from somewhere. Now, there's an obvious question. If white holes expel matter, why don't we see them? If white holes exist in our universe, shouldn't we observe them somewhere, detecting the matter they're emitting? Maybe we do. Some physicists have proposed that certain observed phenomena might be white holes we haven't recognized as such. Gamma-ray bursts, those intense flashes of radiation we discussed earlier, have been proposed as possible white hole events. The brief, intense emission of energy from a point source with no obvious preceding collapse does superficially resemble what a white hole would look like. This is speculative. Most gamma-ray bursts have clearer explanations, but it illustrates that white holes might not be completely absent from our observable universe. They might just be hard to identify. There's also the question of stability. White holes are classically unstable. They're configurations of space-time that can't persist for long. A white hole emitting matter will eventually be covered by its own emissions. The matter coming out will pile up around the white hole, eventually creating enough density to collapse back in, converting the white hole back into a black hole. But if our Big Bang is a white hole, stability doesn't matter. The white hole phase was brief, a transition from the black hole collapse to the expanding universe. It didn't need to persist. It just needed to happen long enough to initiate the expansion to get the new universe started. After that, the expansion itself takes over and the white hole phase is over. The universe we live in is the aftermath of that white hole moment. The expansion we observe is the direct consequence of the quantum bounce and the white hole transition. We're inside what used to be a white hole, still riding the expansion wave that the white hole initiated. And here's the most unsettling implication. White holes are the time reverse of black holes. In a black hole, everything falls in. In a white hole, everything comes out. They're the same object viewed from opposite directions in time. This means our universe's beginning is, in some sense, the time reverse of a black hole's formation in the parent universe. Our Big Bang is the mirror image of a stellar collapse. Our expanding universe is the reverse time version of infalling matter. We're living in an event that, from outside, from the parent universe's perspective, happened in the opposite time direction. This gets deeply strange quickly. Time in our universe runs forward. We experience a clear past and future. Entropy increases. Things age and evolve. But the relationship between our time and the parent universe's time might be complex. Our forward might correspond to the parent universe's inward, the direction matter falls into black holes. If that's true, our sense of time's direction, the arrow of time, the reason we remember the past but not the future, might be related to the direction of gravitational collapse in the parent universe. The reason entropy increases, the reason time has a direction, might ultimately be explained by the fact that we're inside a black hole, and black holes have a natural orientation in time defined by their event horizons. These ideas are speculative. They're at the frontier of theoretical physics. where mathematics and physical intuition push against the limits of what we can currently verify. But they're serious speculations grounded in mathematics explored by serious physicists. White holes aren't just the dismissed mathematical curiosities they used to be. They're increasingly seen as potentially fundamental, as the mechanism by which new universes are born, as the description of what the Big Bang actually was, as the connection between the black hole mathematics we understand and the cosmological observations we've made. The Big Bang was a white hole. Our universe is the expanding interior of what began as a white hole transition. And outside, in the parent universe, someone might be watching a black hole, the same object we experience as our entire cosmos, and wondering what's inside. They'll never know, just as we'll never know what's outside our event horizon. But the mathematics connects us, even across the boundary we can never cross. We're the inside of someone else's black hole. In our beginning, the most fundamental event in our universe's history was a white hole. Nobody told us, because nobody knew, because you can't see inside a black hole, and we're inside one. If the Big Bang was a white hole, does that make our universe feel more or less miraculous? Does having an explanation, a parent universe, a collapsing star, make our beginning feel less special or more connected to a larger reality? We want to know. We've established the basic picture. Black holes create universes. Our universe is inside a black hole. The Big Bang was a white hole transition. Lee Smolin's cosmological natural selection explains why our constants are tuned the way they are. The mathematics connects it all, but we haven't followed the logic all the way down. We haven't asked the question that naturally emerges from everything we've discussed, the question that keeps theoretical physicists awake at night, the question that takes this already unsettling theory and pushes it into genuinely vertiginous territory. If our universe is inside a black hole in a parent universe, what is the parent universe inside? And if the parent universe is inside a black hole in a grandparent universe, what is that inside? And if we follow this chain upward, universe inside black hole, inside universe inside black hole, where does it end? Is there a top? A first universe, a prime mover, a cosmic origin that isn't itself inside something else? The answer, if the theory is consistent, is almost certainly no. There is no top. There is no bottom. It's nested structures all the way, in both directions, infinitely. Welcome to infinite regression, the most destabilizing concept in cosmology. Let's think about what this actually means. Our universe contains billions of galaxies. Each galaxy contains billions of stars. Many of those stars will eventually collapse to form black holes, stellar mass black holes formed from individual stars, supermassive black holes at galactic centers, intermediate mass black holes formed through mergers and accretion. The number of black holes in our universe is enormous. Estimates suggest our galaxy alone contains millions of stellar mass black holes, plus the supermassive black hole at its center. Across billions of galaxies, the total number of black holes in our observable universe is almost incomprehensibly large. If each black hole creates a child universe, our universe has already spawned an enormous number of offspring. Each of those child universes, if they have similar physical constants to ours, thanks to cosmological natural selection, will also form stars, galaxies, and black holes. Each of those black holes creates another generation of universes. The number grows explosively. After just a few generations of universe reproduction, the total number of universes in the family tree becomes astronomical. After many generations, the number exceeds any quantity we can meaningfully describe. An infinite or effectively infinite forest of nested universes, branching with each black hole formation, growing in all directions through cosmic time. And this family tree extends upward as well. Our universe exists inside a black hole in the parent universe. That parent universe presumably also formed inside a black hole in a grandparent universe, because the same physics that applies in our universe should apply in the parent universe. The grandparent universe formed inside a black hole in a great-grandparent universe, and so on upward without limit. Unless, and this is a crucial, unless there's something special about the first universe, some prime mover, some uncaused cause, some universe that didn't form inside a black hole. But there's no obvious candidate for what that universe would look like. No obvious reason why the chain should stop. The mathematics doesn't tell us when to stop. Physics doesn't provide a natural endpoint. So we're left with infinite regression. Universes inside black holes, inside universes, inside black holes, extending upward and downward without limit. An infinite cosmic hierarchy, each level containing the level below and being contained by the level above. What would this hierarchy look like? We can speculate based on what cosmological natural selection tells us. If each generation of universes is selected for black hole production, and if physical constants evolve toward better and better black hole production with each generation, then older universes higher in the hierarchy might have different physical constants than ours, more tuned, more efficient at black hole formation. Our universe might be somewhere in the middle of this hierarchy. Not the most evolved, not the least evolved. Just one node in an infinite network, with ancestors more primitive and descendants more sophisticated, or possibly the other way around, depending on how the evolutionary dynamics work. And every level of the hierarchy is causally isolated from every other. A child universe inside one of our black holes can't communicate with us. Its event horizon prevents information from escaping. We can't communicate with our parent universe. We're inside its event horizon. Each level of the hierarchy exists in complete isolation from the others, unable to send or receive signals, unable to confirm the existence of the levels above and below. This isolation is total. Not just difficult to overcome, physically impossible. The structure of space-time prevents communication across event horizons. Every universe in the infinite hierarchy is effectively alone, surrounded by a structure it can't see or interact with, embedded in a larger reality it can't access. Imagine the philosophical implications. Every universe in the hierarchy might develop intelligent life. Those civilizations would look at their universe, develop physics, discover general relativity, derive black hole mathematics, and find themselves facing the same unsettling possibility we face, that they're inside a black hole, that their universe is one node in an infinite hierarchy, that they can never confirm this because the evidence is forever beyond their reach. Every civilization at every level of the hierarchy faces the same epistemic situation, the same unanswerable questions, the same fundamental isolation. Intelligent life scattered across infinite nested universes, each civilization alone in its cosmic bubble, each one wondering about the levels it can't see. There's something both profound and melancholy about this image. Infinite minds in infinite universes, all asking the same questions, all confronting the same limits. Not communicating, not interacting, not even aware of each other's existence. Just asking independently in isolation the questions that emerge when intelligence confronts the structure of reality. And here's what makes the regression truly vertiginous. Scale has no meaning in this hierarchy. In our ordinary experience, scale matters. Small things are inside big things. A cell is smaller than an organism. A planet is smaller than a star. A star is smaller than a galaxy. Size and containment go together. The container is always bigger than the contained. But in the nested universe hierarchy, this breaks down. A black hole in our universe might appear tiny a few kilometers across for a stellar mass black hole. But the universe inside that black hole could be billions of light years across, containing more space than our observable universe. The container is smaller than the contained. This isn't a paradox, it's a consequence of how space-time geometry works inside black holes. The interior of a black hole is a separate region of space-time, with its own geometry, its own time coordinate, its own spatial extent. It doesn't need to fit inside the black hole as measured from outside. Interior and exterior are different parts of space-time that happen to be connected at the event horizon. So the child universe inside one of our black holes might be larger than our universe. The grandchild universe inside one of its black holes might be larger still. Each generation of the hierarchy could be larger than the previous, even though each is contained within a tiny black hole as measured from outside. Size means something different at each level. The hierarchy isn't like Russian nesting dolls, where each doll is smaller than the one containing it. It's more like, well, it's unlike anything in ordinary experience. A structure where containment doesn't imply relative size, where inside can be larger than outside, where scale as we know it simply doesn't apply. This is deeply disorienting. Our entire intuition about space, about size, about what it means for one thing to be inside another, all of it breaks down in the nested universe hierarchy. We're used to a world where big things contain small things. Here, small things contain big things, and the concepts of big and small lose their ordinary meaning. And yet the mathematics describes it consistently. General relativity allows interior regions larger than their exteriors. The geometry works. It's not paradoxical within the framework of the theory, it's just radically different from everyday experience. There's also the question of time. Our universe has a time coordinate, a direction of increasing entropy, a past and future, a cosmic age we can measure. The parent universe has its own time coordinate. Are these the same time? Are they related? Is our time a subset of the parent's time, or are they independent? The mathematics suggests they're related, but not identical. The formation of the black hole in the parent universe corresponds to the Big Bang in our universe. As the parent universe ages, our universe exists inside a black hole that's part of the parent's history. But the relationship between the two time coordinates is complex. The interior time and exterior time of a black hole aren't simply parallel. This means that from the parent universe's perspective, our entire cosmic history, 14 billion years of expansion, galaxy formation, star birth and death, the emergence of life and intelligence, all of this might correspond to a specific finite period in the parent universe's timeline. a period that might be very short in the parent's time or very long, depending on the relationship between the time coordinates. We're living our cosmic history, and in the parent universe it's all happening during a specific chapter of their story. But we can't know which chapter. We can't know how the two timelines relate. We're inside the black hole, unable to see out, unable to read the parent universe's calendar. And above the parent universe is the grandparent universe, with its own timeline. And above that, the great-grandparent. Each level has its own time, its own history, its own story. And all of these stories are happening simultaneously, in some sense nested inside each other, causally isolated, but mathematically connected. Infinite stories, infinite timelines, infinite civilizations asking infinite questions, all separated by event horizons they can never cross. The regression doesn't end, the chain doesn't stop. The hierarchy extends without limit in both directions, downward into child universes inside our black holes, upward into parent and grandparent universes containing our black hole. And we're somewhere in the middle, neither the beginning nor the end. Just one node in an infinite structure, unable to see above or below, asking questions that the structure itself prevents us from answering. That's the nested universe. That's the infinite regression. That's what follows logically from the mathematics of black holes and the theory of cosmological natural selection. Universes all the way down, universes all the way up, and we're inside one of them, looking outward at our event horizon, unable to see beyond it, wondering what's on the other side. There is no answer. There is no view from outside. There is only the inside always, forever, for every civilization at every level of the hierarchy. We're all inside, every one of us, every civilization, every universe, every level of the structure, inside, always inside, nested, contained, isolated, and the thing containing us is inside something else, which is inside something else, which is inside something else, forever. Does the idea of infinite nested universes comfort you, suggesting existence is eternal and inexhaustible, or terrify you by removing any sense of ultimate foundation or origin? Tell us in the comments. Here's an uncomfortable truth about science. Sometimes the evidence is there before we're ready to see it. Not hidden, not obscure, not buried in impenetrable mathematics, right there, in observations we've already made, in data we already have, and patterns we've already measured. We just weren't asking the right question. The theory that our universe exists inside a black hole isn't just mathematically motivated. It makes predictions. And some of those predictions match observations we've already made, data we've already collected, patterns we've already noticed, but attributed to other causes. We had clues. We ignored them. Or rather, we didn't ignore them, we explained them differently, fit them into the standard model of cosmology without asking whether they might be pointing at something more fundamental. Let's go through the evidence. Not to claim it proves we're inside a black hole, it doesn't, not definitively, but to show that the theory isn't just speculation. It connects to real observations in ways that should make us take it seriously. Start with the flatness problem. Our universe is geometrically flat. When we measure the geometry of space on large scales, looking at how parallel lines behave, how triangles add up, how distances scale with expansion, we find that space is flat to extraordinary precision. Not slightly curved, not obviously curved flat as far as we can measure. This is strange. General relativity allows space to be curved, positively curved like the surface of a sphere, negatively curved like a saddle. Flat is a special case, a knife-edge balance between the two. In the early universe, for space to be this flat today, it had to be even flatter than extraordinarily, precisely, almost impossibly flat. A tiny deviation from perfect flatness in the early universe would have grown over time into obvious curvature today. Why is space so flat? Standard cosmology invokes inflation, a period of exponential expansion in the early universe that would flatten out any initial curvature. Much like inflating a balloon makes its surface appear flatter, inflation works mathematically, but it requires specific conditions and a specific field, the inflatened field that we've never directly detected. The black hole universe theory offers a different explanation. If our universe formed inside a black hole through a quantum bounce, the geometry of the resulting space-time would naturally be flat or very nearly flat. The bounce process doesn't produce arbitrary geometries. It produces specific geometries determined by the physics of the bounce, and the geometry it produces tends to be flat. So flatness, which standard cosmology explains through inflation, might instead be a direct consequence of our universe forming inside a black hole, not a fine-tuned initial condition requiring an inflattened field, just a natural outcome of the formation process. Then there's the horizon problem. The cosmic microwave background, the leftover radiation from the early universe, the afterglow of the Big Bang is uniform, remarkably, eerily uniform. In every direction we look, it has almost exactly the same temperature. Not almost the same, almost exactly the same, varying by only tiny fractions of a degree. This is strange because regions of the sky that we observe in opposite directions were never in contact with each other in the early universe. They were separated by distances so vast that light couldn't have traveled between them before the microwave background was emitted. Yet they have the same temperature. How did they reach the same temperature if they could never exchange heat? Standard cosmology again invokes inflation. Before the inflationary expansion, all regions of the universe were in contact. They were close enough together that they could exchange heat and reach thermal equilibrium. Then inflation expanded them to the distances we observe today. The uniformity is a relic of that pre-inflation equilibrium. But the black hole universe theory offers an alternative. If our universe formed from matter that was in thermal equilibrium inside the parent universe's black hole, it would naturally begin in a uniform state. The uniformity of the cosmic microwave background would be inherited from the conditions in the parent universe, not generated by a pre-inflationary period of equilibrium. Again, not proof, but a different explanation for the same observation. An explanation that emerges naturally from the black hole formation picture without requiring inflation. And then there's dark energy, the mysterious force driving the accelerating expansion of our universe. We observe that distant galaxies are accelerating away from us, not just moving away due to the initial expansion, but accelerating as if being pushed apart by some energy embedded in the vacuum of space. We call this dark energy because we don't know what it is. It constitutes the majority of our universe's energy budget, far more than all the matter, ordinary and dark, combined. It's not associated with any particle we've detected. It doesn't cluster like matter. It's uniformly distributed, constant over time, filling all of space equally. In the black hole universe picture, dark energy might have a natural explanation. The event horizon of the black hole surrounding our universe has thermodynamic properties. It has energy associated with the Hawking-Gibbons temperature of the horizon. This energy is distributed throughout our universe, coming from the horizon, filling space uniformly. This sounds exactly like dark energy. A uniform energy associated with the cosmological horizon, distributed throughout space, not associated with particles or matter just there, as a property of the boundary that surrounds our universe. If dark energy is the energy of our event horizon, the horizon of the black hole we're inside, then it's not mysterious at all. It's a direct consequence of our situation. We're inside a black hole. Black holes have event horizons. Event horizons have thermodynamic properties. Those properties manifest from the inside as a uniform energy filling space. Dark energy might be the fingerprint of our prison, the evidence of our event horizon, detectable from inside, manifesting as the force driving cosmic acceleration. This would be remarkable. One of the deepest mysteries in cosmology: what is dark energy? Why does it have the value it is might be explained by the simple fact that we're inside a black hole? The value of dark energy would be determined by the size and properties of our black hole, not by some arbitrary constant we can't derive from first principles. And then there's the most direct evidence of all, the cosmological constant problem. Quantum field theory predicts that empty space should have enormous energy. Virtual particles pop in and out of existence in the vacuum, contributing energy that should show up as a cosmological constant, an energy associated with empty space driving expansion. The prediction from quantum field theory is an energy density so enormous that it would cause the universe to expand, so fast that galaxies, stars, and atoms couldn't form. But we observe a cosmological constant that's many orders of magnitude smaller than the quantum field theory prediction. This discrepancy between what quantum mechanics predicts and what we observe is one of the worst predictions in the history of physics. Something cancels out most of the predicted vacuum energy, leaving only a tiny residual that we observe as dark energy. Why? What cancels it? The standard model of physics doesn't have a good answer. The black hole universe picture might. If our universe's vacuum energy is determined not by quantum field theory alone, but by the properties of our event horizon, by the fact that we're inside a black hole with specific properties, then the value of the cosmological constant might be fixed by the black hole's parameters rather than by vacuum energy calculations. The event horizon somehow suppresses or regulates the vacuum energy, leaving only the small observed value. This isn't worked out in detail. It's not a complete solution to the cosmological constant problem, but it points toward a different framework for understanding the problem, one where the answer comes from our cosmological situation rather than from particle physics alone. Beyond these specific observations, there's a more general point. The standard model of cosmology, the lambda-CDEM model, which includes dark matter, dark energy, and inflation, is extraordinarily successful at fitting observations. It works. It predicts the cosmic microwave background, the large-scale structure of the universe, the abundances of light elements. It's not wrong, but it requires several ingredients we don't understand. Inflation: what is the inflatoned field? Dark matter: what particle is it? Dark energy: what is it? The cosmological constant: why does it have this value? These aren't minor puzzles. They're foundational mysteries. We've built a highly successful model that works empirically but contains several components we can't explain from first principles. The black hole universe theory might explain some of these components. Not all of them. It's not a complete alternative cosmology, but it offers natural explanations for flatness, for uniformity, possibly for dark energy, possibly for the cosmological constant. Explanations that emerge from the basic picture: our universe formed inside a black hole without requiring additional unexplained ingredients. That's scientifically valuable. When a theory explains observations that other theories require additional assumptions to explain, that's evidence in the theory's favor. Not proof evidence, a reason to take the theory seriously. We had clues all along: the flatness of space, the uniformity of the microwave background, the existence and value of dark energy. These aren't random observations. They're telling us something about the initial conditions and boundary conditions of our universe. And one interpretation of what they're telling us is, you're inside a black hole. The initial conditions came from the parent universe. The boundary conditions are your event horizon. The dark energy is the horizon's energy, felt from the inside. We didn't see it because we weren't looking for it. We were fitting data to models, explaining observations with theoretical constructs like inflation and dark energy, building a successful cosmology without asking the deeper question: why does our universe have these specific features? The answer might be because of how it formed. Because it formed inside a black hole in a parent universe through a quantum bounce that naturally produces flat, uniform space. Because it's bounded by an event horizon whose properties we feel as dark energy. The evidence was there. The clues were present. We just interpreted them differently. Maybe it's time to reinterpret. Which piece of evidence do you find most compelling? The flatness, the uniformity, or dark energy as horizon energy? Or does none of it feel convincing yet? Let us know below. We've covered the mathematics. We've explored the theory. We've looked at the evidence. Now comes the hardest part, not the physics, not the equations, not the observations, the implications. Because if this theory is right, if our universe genuinely exists inside a black hole, if black holes create universes, if we're embedded in an infinite hierarchy of nested realities, then almost everything we thought we knew about our place in existence needs to be reconsidered. Not just cosmology, everything. Let's start with the most fundamental implication, the origin question. Humanity has always asked where everything came from. Every culture, every religion, every philosophical tradition has wrestled with this question. What was there before the universe? What caused the Big Bang? Why is there something rather than nothing? Standard cosmology pushes the question back to the Big Bang and stops. The Big Bang is the beginning of time, not just the beginning of the universe, but the beginning of time itself. There's no before the Big Bang because time didn't exist before it. The question, what caused the Big Bang, is grammatically meaningful, but physically meaningless. Like asking what's north of the North Pole. This answer is unsatisfying. Not because it's wrong, it might be right, but because it terminates inquiry. It says here is the wall. You cannot go further. The question has no answer. The black hole universe theory does something different. It doesn't terminate the question, it transforms it. What caused our Big Bang? A black hole formation in the parent universe. What caused that parent universe? A black hole formation in its parent universe, and so on infinitely upward. This doesn't ultimately answer the question. Infinite regression doesn't resolve why anything exists rather than nothing, but it transforms the nature of the question. Instead of a wall, we have a corridor infinite, extending beyond sight in both directions, but a corridor we can at least conceptually traverse. And there's something intellectually more honest about a theory that says it goes back forever and we don't know where it ends, versus a theory that says here is the beginning and there is nothing before it. Both face the same ultimate mystery. Why is there something rather than nothing? But one admits the mystery more openly. Then there's the question of uniqueness. Are we special? Is our universe unique, or just one of many? The black hole universe theory gives a very clear answer. We are not special. Our universe is one node in an infinite network, one generation in a cosmic family tree that extends infinitely, one bubble among uncountable bubbles, each containing its own galaxies, stars, planets, possibly civilizations. This is the most radical dethroning of cosmic centrality imaginable. Copernicus showed we're not at the center of the solar system. Hubble showed we're not at the center of the galaxy. Cosmology showed we're not at the center of the universe. Now, the black hole universe theory suggests we're not even in the main universe. We're inside a black hole, one of countless black holes in a parent universe that's itself inside a black hole. We're nested, embedded, contained. At every scale, we're not at the center of anything. We're inside something, and that something is inside something else. The cosmic address gets longer. Planet Earth, solar system, Milky Way galaxy, local group, Virgo supercluster, observable universe, inside a black hole, in a parent universe, inside another black hole, in a grandparent universe, and so on forever. An address that extends infinitely, a location that can never be fully specified, a position that is simultaneously knowable at local scales and utterly unknowable at cosmic scales. But here's the flip side. If we're not unique, if universes are common born from every black hole, existing in infinite numbers, then the fact that our universe has the properties it does becomes more comprehensible. We're not a miracle. We're one configuration among infinite configurations, selected by cosmological natural selection to be good at making black holes, and incidentally good at making complex structures and life. Our existence doesn't require a creator. It doesn't require fine-tuning by design. It requires only that universes reproduce, vary, and are selected. The same blind process that explains biological complexity explains cosmic complexity. No miracle required, just evolution operating at cosmic scales. This has profound implications for how we think about purpose and meaning. If the universe wasn't created for us, if we're a side effect of black hole optimization, if our existence is explicable through natural processes without invoking design, then meaning can't come from the universe's purpose. The universe has no purpose in this framework. It just evolves. But meaning doesn't have to come from cosmic purpose. Meaning can come from what we do, what we experience, what we create. It can be self-generated, self-sustaining, internal, rather than external. The universe's indifference doesn't diminish the significance of consciousness, of love, of curiosity. It just relocates where significance comes from. It comes from us, from the fact that we're aware, that we experience, that we ask questions the universe itself doesn't ask. We're not the universe's purpose, but we might be the universe's way of understanding itself, at least in our tiny corner of the infinite hierarchy. Now consider what this theory means for physics itself. One of the great projects of modern physics is the unification of quantum mechanics and general relativity. These two theories are both extraordinarily successful. Quantum mechanics describes the very small. General relativity describes the very large, but they're mathematically incompatible. They can't both be exactly right. A deeper theory must underlie both, reconciling their apparent contradictions. The black hole universe theory suggests that this reconciliation must happen at singularities, at the places where black holes form and bounce into new universes. The quantum bounce that creates a new universe is precisely where quantum gravity operates, where quantum mechanics and general relativity must work together. Understanding the black hole universe theory, working out its details, understanding the quantum bounce mechanism, this might be the path to quantum gravity. The theory of everything, the unification of physics, might be found not by looking for new particles or new forces, but by understanding what happens at the singularities where universes are born. The biggest questions in fundamental physics, quantum gravity, the cosmological constant, the nature of time, the origin of physical laws, might all have answers that emerge from understanding what happens when a black hole creates a universe. And then there's the question of physics itself. Why do the laws of physics take the form they do? Why these laws rather than others? Why does quantum mechanics govern the small and general relativity govern the large? Why do these specific symmetries and forces and constants exist? Standard physics treats the laws as given. They're what they are. We discover them, we describe them, but we don't explain why they are what they are. It's like asking why mathematics is consistent. It just is. But cosmological natural selection suggests the laws of physics aren't fixed eternal truths. They evolved. They're the product of selection over many generations of universe reproduction. They take the form they do because those forms are good at producing black holes, which produce more universes with similar forms. The laws of physics are the genetic code of universes. They're inherited, they mutate slightly with each generation, and they're selected for reproductive success. They're not eternal platonic forms, they're evolutionary adaptations. This is a radical reconceptualization of what physical law is. We've always thought of the laws of physics as discovered, as truths existing independently of our observation, as the fundamental structure of reality. The black hole universe theory suggests they're more like biological traits evolved, contingent, functional, rather than necessary, good enough rather than perfect. Different universes have different laws. Not radically different cosmological natural selection keeps them close to the parent universe's laws, but different enough that chemistry might work slightly differently, stars might form and die differently, the range of complex structures might be wider or narrower. Our laws aren't the only laws. There are laws, the laws of our particular universe, inherited from our parent universe with small mutations, selected because they work well for black hole formation. Other universes have other laws, other physical realities, other chemistries, other forms of complexity we can't imagine because they operate by rules we've never encountered. The implications for the search for extraterrestrial life are also significant. If universes are common, if every black hole creates a universe, then the question of whether life exists beyond Earth becomes almost trivially obvious. In an infinite hierarchy of universes, each containing billions of galaxies and trillions of stars, life almost certainly exists in countless places. Not just in our universe, in the parent universe, in the child universes, in every generation of the hierarchy. But we can never contact any of it. Not just the life in other universes also, potentially, the life in our own universes, child universes. They're sealed inside black holes, causally disconnected from us. And life in the parent universe, if it exists, is similarly isolated, unable to send information across our event horizon. We're surrounded by life, possibly. In an infinite nested structure, intelligence might be common, but we're isolated from all of it by event horizons we can never cross. The most profound loneliness imaginable, surrounded by others in an infinite structure, yet unable to communicate with any of them across the boundaries that separate levels. And finally, consider what this means for the future. Our universe will eventually produce more black holes than it has produced so far. Stars will continue to form and die. Supermassive black holes will continue to grow. Each new black hole is a new universe, a new branch in the family tree, a new generation of the cosmic evolution. We're not at the end of the universe's reproductive career. We're in the middle of it. Billions of child universes have already been created inside our black holes. Billions more will be created in the future. The family tree is still growing, still branching, still producing descendants. And those descendants, the universes inside our black holes, might already contain life. Right now, inside a stellar mass black hole somewhere in our galaxy, a universe might be expanding, billions of years into its own history. Stars might be shining there, planets might be orbiting. Life might be thinking about why its universe has the properties it has, and they might be reaching the same conclusion we're reaching, that they're inside a black hole, that their universe formed from a parent universe, that they're one node in an infinite hierarchy, and they can no more contact us than we can contact them. The universe is full of minds, possibly, all of them isolated, all of them asking the same questions, all of them surrounded by event horizons they can't cross, all of them inside, always inside, and outside each of them another inside, forever. If the laws of physics are evolved rather than fixed, if they're contingent, functional, not necessarily true, does that change how you think about science? About reality? About truth itself? This is one of the deepest implications of the theory. Tell us what you think. We started with a simple, unsettling question. What if we're inside a black hole? What if the universe we call home, the cosmos we've mapped, measured, explored, and marveled at is itself contained within something larger, something we can never see or reach or escape from? And we found that this question isn't just philosophical speculation. It's grounded in mathematics. It emerges from equations we trust, from physics we've tested, from observations we've already made and interpreted differently. The theory that our universe exists inside a black hole is serious, supported, and deeply, profoundly unsettling. Let's recap what we found. The mathematics of black holes and the mathematics of the Big Bang are eerily similar, enough that physicists had to ask whether they're describing the same event. The singularity at the start of our universe and the singularity inside a black hole are mathematically identical objects. The boundary of our observable universe behaves like an event horizon, a one-way information barrier surrounding us, isolating us from whatever lies beyond. These Smolin showed that if black holes create universes, and if physical constants change slightly with each generation, then universes evolve through natural selection. They get better at making black holes. They accumulate properties conducive to complexity, and the constants of our universe, the specific values of gravity, of nuclear forces, of electromagnetism, are consistent with a universe that's been selected for black hole production. We might be the product of cosmic evolution, descended from a long line of universes that got progressively better at reproducing. White holes, the mathematical mirror images of black holes, long dismissed as unphysical, might be what the Big Bang actually was. Not creation from nothing, but creation from something. Matter from the parent universe transformed through quantum bounce, expelled as a new expanding space-time. Our beginning was someone else's black hole. Our universe is the inside of a gravitational collapse. The hierarchy extends infinitely. Universes inside black holes, inside universes in both directions without limit. No first universe, no final universe. Just an infinite nested structure, each level causally isolated from every other, unable to communicate, unable to confirm the other's existence. An infinite family tree of universes, branching with every black hole formation, growing without bound through cosmic time. And the evidence was there all along. The flatness of our universe, the uniformity of the cosmic microwave background, the existence and value of dark energy. All of these puzzles, things we've observed, measured, confirmed, and struggled to explain, fit naturally into the black hole universe picture. Not coincidences, not unexplained anomalies requiring extra theoretical machinery. Natural consequences of our cosmological situation. We formed inside a black hole, we're bounded by an event horizon, we inherited our initial conditions from a parent universe. Nobody told us, because nobody could know. Because from inside a black hole, things look normal. Physics works. Space extends, time passes. The universe is vast and beautiful and comprehensible. You can live your entire life, build a civilization, develop science, reach the frontiers of knowledge, and never know you're inside a black hole. Because being inside a black hole for the inhabitants of the universe within it looks exactly like being in a universe. It looks like this. And here's what I find most remarkable about all of this. Not the physics, though the physics is extraordinary. Not the mathematics, though the equations are beautiful. But the fact that we can know that we can sit here inside a black hole and figure out that we're inside a black hole. That the same intelligence that emerged from the universe's physics can turn around and analyze that physics, can follow the mathematics to its disturbing conclusions, can confront the unsettling reality of our cosmic situation. We're made of matter that formed in stars in a universe that might be inside a black hole, that might be one generation in an infinite evolutionary chain of universes. We're the product of cosmic selection, descendants of a long line of universe ancestors, inhabitants of a bubble bounded by an event horizon we can never cross. And we know this, or we suspect it. We've followed the mathematics and arrived at this picture. We've looked at the observations and found them consistent. We've asked the questions that lead here. That's not nothing. That's extraordinary. That matter can organize itself into patterns capable of understanding the structure they're embedded. In that consciousness can arise from physics, and then look back at physics and comprehend its own origins. That's perhaps the most remarkable thing in the universe, or in any universe. The black hole universe theory, if true, doesn't diminish us. It contextualizes us. We're not the purpose of the universe, we're a consequence. We're not at the center of existence, we're inside one level of an infinite hierarchy. We're not the only universe, we're one of countless, each one sealed in its own black hole, each one unable to communicate with the others. But we're here, we're aware. We're asking questions that the universe itself doesn't ask, because the universe, for all its vastness and complexity, doesn't wonder about itself. Only we do. Only consciousness does. Only matter organized into minds can look at the cosmos and ask, what is this? Where did it come from? What are we inside? The answer might be a black hole, and that black hole is inside a universe, and that universe is inside another black hole, all the way down, all the way up, without beginning or end. We live in a cosmic prison with walls made of space-time. Our bars are event horizons. Our universe is a cell in an infinite structure we can never fully map, but it's a cell with stars, with galaxies, with billions of years of history and billions more to come, with physics beautiful enough to describe itself, with mathematics capable of revealing its own structure, with consciousness able to contemplate its own situation. We're inside a black hole. We've always been inside a black hole. We'll always be inside a black hole. And somehow, despite that or because of that, we're here, thinking, wondering, reaching toward understanding, even when understanding reveals that the full picture is forever beyond our reach. The walls of our prison are made of the most beautiful mathematics ever written. The bars of our cage are event horizons described by equations of breathtaking elegance. Our jailer is the universe itself, indifferent, vast, extraordinary. And we're not just prisoners. We're the part of the prison that became aware it was inside something. The part that looked at the walls and understood what they were. The part that said, I see what this is. I understand the structure. I know where I am. We're inside a black hole. And knowing that, truly knowing it, understanding what it means, following it to its conclusions, is perhaps the most human thing we've ever done. We looked at the universe. We followed the mathematics. We arrived somewhere dark and strange and beautiful. And we're still here, still looking, still following the equations wherever they lead. That's what we do. That's who we are. Inside a black hole, looking out forever